Welcome, and thank you for joining us. My name is Joe Staller, and I am a Senior Research and Development Chemist at Epic Resins in Polymers, Wisconsin. Today, I invite you to join us while we discuss managing heat through proven e-mobility polymers and how adjusting the thermal properties of a polymer can influence other properties of the polymer. To start, I'd like to share a little about Epic Resins. Epic is a formulator of high-performance epoxy and polyurethane thermoset polymer solutions. We have been developing and manufacturing polymer solutions for industry for over 65 years. Our research and development lab and manufacturing is located in Polymers, Wisconsin, conveniently situated between Chicago and Milwaukee, as you can see on the map. We manufacture over 3,000 different products and service 1,500 customers domestically and internationally from this location. Epic Resins is ISO 9001, 14001 certified, as well as OSHA Sharp certified. When working with Epic Resins, our customers gain access to our technical sales force, as well as our research and development chemists. We believe that access to our development chemists and our development lab capabilities acts as an extension to your design team. This level of support to your project helps you achieve the results in condensed timeframes to shorten your time to market. Before we begin to discuss different polymer solutions and how they manage heat, I would like to introduce a few details about thermal transfer. There are four main modes of how thermal energy is transferred. These are convection, radiation, phase change, and conduction. The primary mode of thermal transfer in polymers is through conduction. Today, we will discuss a few details that influence the thermal conductivity of a polymer. If you are interested in learning more about the variables that affect thermal conductivity of polymers, please see our webinar titled Solving Formulation Challenges of Thermally Conductive Materials in E-Mobility in the webinar resources section of this webinar or on our YouTube channel. Conduction is the main form of heat transfer in polymers. Thermal conduction in solids is dictated by a waveform called a phonon. A phonon in polymers and solids are a collective excitation of molecules, causing a waveform very similar to a sound wave. The efficiency of a phonon in a solid is dictated by the excitation kinetics of the molecules. Thus, improving the kinetics of the molecules in the polymer will improve the efficiency of phonon waves in the polymer, and hence increase thermal conductivity. Generally, polymers have a lower thermal conductivity than metals and minerals. These videos show how a polymer's excitation kinetics are less uniform than metals and minerals, which is why they have lower thermal conductivity than metals and minerals. So, how do we optimize the thermal conductivity of a polymer? We do this by modification to three properties of the polymer formula: polymer structure, filler type and loading, and particle size. It is important to remember that these modifications can also affect other vital properties of the formula. We will discuss this in more details in the applications highlights section of this webinar. First, we will discuss the polymer structure and how thermal conductivity is affected through the polymer structure. We formulate at Epic Resins from a molecular structure to property relationship. Ultimately, we utilize our knowledge of molecular structure and the properties it imparts in the final polymer. Many polymers have an amorphous structure that tend to hinder phonon resonance, as we discussed and demonstrated in these videos that I played in the previous slide. When we build a more uniform structure in the polymer, we improve the molecular kinetics and phonon efficiency. In polymers, we do this by increasing crystallinity and cross-link density into the molecular structure. This improves phonon resonance and hence thermal conductivity. In these images of amorphous crosslink and crystallinity, you can see the differences between that amorphous structure, cross-link structure and having higher crystallinity. However, the most significant improvement to thermal conductivity in a polymer comes from the use of mineral fillers. There are many mineral fillers used, and each has different properties that they impart to the final polymer. All will improve thermal conductivity, but some more than others. You will see a comparison of these properties when we discuss products in the applications highlight of this webinar. As each of these fillers are utilized in the polymer, the efficiency of their use is dependent upon designing the proper particle size distribution. For thermal conductivity, kinetics is crucial. To illustrate this, I have 3 different sets of marbles to show you. This first picture shows lots of large marbles, showing lots of interstitial space between each of the marbles. This second picture shows smaller marbles, but still a significant amount of interstitial space. This last group of marbles is a mixture of many sizes. You can see the marbles have much better contact with one another. This marble example helps to demonstrate that particle size distribution helps to optimize particle contact and loading in order to improve overall kinetics and thermal conductivity. The use of thermally conductive polymers in e-mobility is crucial for the implementation of technologies we depend on. Many of these technologies exist within 2 of the primary applications in e-mobility: power electronics and electric motors. The application of polymers in power electronics includes inverters, battery management systems, DC to DC converters, voltage control modules, etc. In all these applications, thermal conductivity is vital, but there are other peripheral properties that will be influenced by modification to the thermal conductivity of the polymer. We will be discussing these in this webinar of viscosity, flammability, CTE and TG, as well as electrical properties. Viscosity is one critical property that can be drastically affected by thermal conductivity accomplished through filler loading. In this video, you can see how viscosity affects flow around electrical components. Notice how all the components are well coated with the flow of the polymer. Flow is essential to accomplish complete contact between vital thermal components and the heatsink. Poor flow results in poor contact with components, resulting in air gaps that cause a thermal insulating condition instead of a thermal conducting condition. Thus, it is important to consider both viscosity and thermal conductivity when choosing a polymer for your application. A great example of this can be found in the diversity of different products that we offer. Looking at S7593, which has a thermal conductivity of 3 watt per meter Kelvin. This product is designed as a unique alternative for thermal gap pads, where the application needs high thermal conductivity and self-leveling, but can be applied in a specific location. S7512, on the other hand, has a lower thermal conductivity of 1.33 watt per meter Kelvin. But as you can see, it has a viscosity of 4 to 5,000 centiploids and is significantly lower in viscosity. S7512 is designed to flow similar to what I showed you in the last video, whereas the 7593 is designed to be applied directly to the site where it is required. In most all electrical applications, some level of flame mitigation is required. One of the most common standards is the UL 94 standard. This diagram shows the general setup of the UL 94 vertical burn test. This video shows how the test is conducted. We set a Bunsen burner to the specified flame intensity. We then set incident of the flame to the sample at 10 millimeters and burn the sample 2 sequential times for 10 seconds each. The total self-extinguish time for each burn must be below 10 seconds for the sample to pass at that thickness. We offer many different options when it comes to flammability ratings. In most polymer classifications, there are some level of mutual exclusivity in flammability rating and thermal conductivity. The reason for this is that the fillers that give the best flammability ratings generally have lower thermal conductivity. You can see this in comparing the 7593 to the 7553. 7593 has a significantly higher thermal conductivity, but has twice the thickness in its UL rating. This is an indication of the different type of filler utilized to accomplish thermal conductivity versus a thinner flame rating. Another important thermal property to consider when selecting a polymer is the coefficient of thermal expansion, also known as the CTE, and the glass transition temperature, or the TG. The CTE is the rate of expansion over a temperature range, and the TG is the temperature where a material changes from a hard and rigid glass type material to a soft, pliable material. We measure these properties on a thermomechanical analyzer, also called a TMA. The TMA functions by using a quartz probe to measure the height of a sample. So in this video, you see that black square, that is the sample, and then on top of it is sitting a quartz probe. That quartz probe goes down into the chamber, goes from a very cold temperature to a warm temperature, and that's how the instrumentation itself works. This is the graphic result of a TMA. At the low temperature portion of this graph on the left, you see the pre-TG CTE from -40 to 0 degrees C of 61 ppm. As the temperature increases to the right, we see an inflection point on the graph at about 60 degrees C. This is the TG. Below this temperature, the polymer is considered a rigid polymer, and above this temperature, the polymer is a soft, pliable polymer. To the right of the TG, you see the post-TG CTE, measured between 75 and 106 degrees C at 170 ppm. The post-TG CTE is typically higher than the pre-TG CTE. It is important to understand where the TG of the polymer is relative to your operating temperature range to reduce component stresses that occur in this thermal transition. Each application within power electronics has different operating temperature ranges and different optimum TG and CTEs. It is typical that applications with sensitive components and vibration conditions will find greater longevity with low TG products like S7593, RM2018, and S7553. All of these products have a TG below -50 degrees C, which is below most outdoor applications. This means that the polymer will maintain a soft and vibration-resistant hardness during this life cycle. This will protect sensitive components from expansion, contraction, as well as vibration and impact. TG is not generally affected by filler loading, making highly thermally conductive, low TG polymers like the 7593 possible for high-performance applications. Power electronics can process large amounts of energy at very high voltages, making dielectric strength a critical property to analyze for a polymer. At Epic Resins, we leverage our high-pot dielectric tester to analyze dielectric strength. We do this by placing a polymer sample between two electrodes submersed in a dielectric oil test chamber. The high-pot tester then ramps the voltage between the electrodes that are sandwiching the polymer to 50,000 volts or failure. As the powerhouse of e-mobility, electric motors put the greatest demand on polymers. Whether it is an IPM SYN RM or an axial motor, complete encapsulation or secondary insulation, polymers are a vital protective component to motor applications. This polymer protection starts with having the correct coverage of vital components. Viscosity is one of the primary properties that affects this protection. As we discussed during the power electronics portion of this webinar, viscosity and flow are crucial to ensuring encapsulation and protecting your components. However, we also learned that an increase in thermal conductivity also results in an increased viscosity. Looking at the viscosity of O227 in the table below compared to the O230, you can see that the viscosity is more than double for the O227, but so is the thermal conductivity. The effect of increased viscosity on flow can be mitigated with process controls used in the motor industry. The polymer systems used in motor applications generally require heat curing, which we will discuss in a subsequent section. This heat curing process has a dramatic effect on the viscosity and flow. This video gives you a visual representation of how heat affects viscosity. These are both the same product with the same viscosity at 25 degrees C, but the can on the left was heated to 50 degrees C and the can on the right was at 25 degrees C. This shows very simply the reduction in viscosity and increase in flow with higher temperatures. This graph shows the quantitative data of how temperature affects viscosity. On the left side of the graph, the viscosity is 85,000 centipoise at 25 degrees C. As the temperature increases to the right to 45 degrees C, you can see that the viscosity dramatically drops to below 10,000 centipoise and continues to drop below 5,000 centipoise at 65 and 55 degrees C. Utilizing elevated temperature to reduce viscosity and improve flow is a common implemented process control to ensure encapsulation and protection of motor windings and motor components. Electric motors run at higher temperatures for longer durations than most of the components of an EV. These conditions require a polymer to not only have higher thermal conductivity, but also excellent thermal resistance. We can accomplish both of these properties simultaneously by increasing the cross-link density and utilizing thermally conductive fillers. In motor applications, an added benefit to high filler loadings is lower CTE. Comparative, when we look at the table below, we can see that O227 has a 16 to 20% lower CTE than O230 due to its higher filler loading. A lower CTE results in lower stress on the windings during thermal cycling, giving greater longevity to the motor. The curing process for motor polymers can vary depending on the chemistry of the polymer being used. However, one process requirement that all polymers have is that they must be processed to the TG temperature in order for the polymer to attain full cross-link density. This is a vital step in the process to ensure the polymer will have the thermal properties required to maintain protection of the motor components. Additionally, the polymer must be at the temperature for the prescribed time, not just in the oven for that time. Motors are large heat sinks and require added time to bring the metal parts up to temperature during the curing time. Step curing processes are also utilized to reduce shrinkage during the curing process. Generally, step curing processes are utilized for large masses or large motors that will have more exotherm during that curing process. E-mobility motor propulsion is evolving to utilizing higher and higher voltages. This translates into polymers required to insulate higher and higher voltages. Combining high thermal conductivity and high dielectric strength are two of the greatest benefits of polymers. However, filler type can significantly change the electrical properties. S7613 has a dielectric constant of over 1200 volts per mil, with a thermal conductivity of 0.5 watt per meter Kelvin. When we compare this to the O227 with a dielectric strength of 300 volts per mil and a thermal conductivity of 2 watt per meter Kelvin, these two products contain different fillers, which show in the difference in these properties. Each of these products are developed for different applications that prioritize different properties. O227 was designed for a low voltage, high current motor to maximize thermal conductivity and cooling, whereas the S7613 was developed for high voltage, fast switching motors. Thermal polymers are an essential resource to provide flexibility to optimize the performance and requirements for your e-mobility application. I hope this webinar has given you some insight into managing heat through proven e-mobility polymers. Thank you for your time, and please connect with us through the information below. See you next time.